As promised, this is the third lecture on timer instructions. There is only one timer data type, but there are 4 instructions if you want to count the reset. But basically there's 3 timer instructions but 1 timer data type. So the data type is the object of the timer instructions. So each of the 3 instructions, TON, TOF, RTO, they instruct the execution of that timer data type slightly different. So now we're going to do the retentive on delay timer, which is basically an on delay, but it doesn't reset when the run goes false. You have to reset it with a reset instruction. So let's look at this lab. Next up, RTO, retentive on delay timer, or delay retentive timer on. This is where we ended with our previous project. I also went over the idea of moving your menus and toolbars around to give you more vertical space for your code. I mainly do this because I realize some of you may be watching these videos on a mobile device and you don't have 27-inch high-def screens like I typically use. But I do record these in 1080p, at least 720p. Save your project, beginner, L, your processor number, TON _ RTO. Up here we haven't done that yet. File, save as, and we'll change that to RTO for retentive timer on delay. We're going to replace the TOF with a TON. So I think I'll go offline because it's easier to do this offline than online. Go up here and make that a TON. And we'll give it 10,000 milliseconds. Now with RSLogix 500, if you make this kind of a change, which you can't do it as directly as you can in 5000, and then down here we're going to make this in RTO. You can double click, you can type in RTO, or you can drill down and select the RTO. See the question marks pop up. Okay, we edited the TOF to be a TON and the TON to be an RTO to compare the 2 instructions. Now we could have left the bottom one a TON and made the top one the RTO, but the TON is really our anchor point for timer instructions that are used with the timer data type. I would say that TONs are used 1,000 to 1 to RTOs and probably 10,000 to 1 to TOFs. TON is the timer instruction that you will see the most often in the field. And we also needed to change this to an XIC and this to an XIC. Now we're going to download. We're going to save first. And since we've already named it TON RTO, we don't have to change the name, we can just save. Then communications, who active. Select the processor, download. First thing I want to point out is after I edited this code and downloaded it, see we're in the remote run mode, look at the done bit. Remember this was originally true if off when this was a TON that we inverted to make it behave like a TOF. And this is not part of the course, but if I see anything that I think is unusual, I like to point it out and explain it when it happened. I went online and looked, the done bit is set. That's because the done bit was set on that instruction and we never reset it. We changed it to an RTO, so the last thing my time also heard, remember this is a timer data type, that's not a timer. My time also is a timer data type. It's just a information object. It's an instance of the timer data type. It doesn't know TON from TOF from RTO. So the last thing that timer data type was told is that its done bit was on. So we changed all the logic, downloaded, went online, and look, the done bit's set, but the accumulate doesn't equal the preset. So that's what I call data table carnage. Now, if this were a TON and the done bit was set, as soon as this rung was scanned, the false condition would clear the accumulate, clear the enable bit, and clear the done bit. Not so with an RTO because it is retentive. So that's very interesting. Right off the bat, we have something interesting to look at. And what we're going to compare here is output 0,1 against 2,3. Now, we don't want them to behave the same because we are comparing a timer on delay with a timer on delay that is retentive. Now, the only way that we could clear the done bit on a timer data type that has an RTO working against it or with it is we would have to use the reset instruction. Because an RTO, when it's done and it just sits there. You can go false, true all you want. On the rung, it's not going to change anything because it's retentive. It retains wherever it was at when you change the state of the rung condition out from this instruction. So, switch input 0 to the on state. Look at the next, and I tell you, look at the next set of questions first. Before I do that, I'm going to do what you should have done, and I'm going to look at the next set of questions. Are both timer data types accumulating 1/1000ths of a second? Are both of the timer instructions setting the timer timing bit to 1? Did both of the instances of the timer data type reach an accumulation that equaled the preset? Did the done bit set to 1 when the accumulation of both instances of the timer data type equaled the preset? Do you see any hint of a difference in behavior between the result of a TON addressing a timer data type and an RTO addressing a timer data type from the instant you enable them until their accumulates equal their presets and the done bits set to 1? If you read through those questions, then you kind of know what to look at. Now, since this should not have been set to done, it may cause a problem. So rather than gamble on that, I'm going to right click, toggle bit to get this in the reset condition, because this is what it should have looked like for you, just like this. If for some reason you ended up with this on, like that, well then clear it and start over. Start back right here. So we're going to turn it on, and what you're going to do is you're going to watch the accumulate values in both timer data types and the timer timing and done bits. And this is 10 seconds, so you've got plenty of time to watch. So you see timer timing are both on. They're both accumulating at the exact same rate. And when they time out, the timer timing bits go off and the done bits go on. So if we look at those questions, are both timer data types accumulating? Yes. Are both of the timer instructions setting the timer timing bit to 1? Yes. Did both of the instances of the timer data type reach an accumulation that equal the preset? Yes. Did the done bit set to 1 when the accum of both instances of the timer data type equal the preset? Yes. Did you see any hint of a difference in behavior between the result of a TON addressing a timer data type and an RTO addressing a timer data type from the instant that you enabled them until their accumulates equaled their presets and the done bits were set to 1? No, you should not have seen any difference. Now here's a caveat. If I set input 0 back to the off state, which is the next thing you did, well, now we have a difference, don't we? Now we're right back where we started when I downloaded and the done bit was already set. Do you see any hint of a difference in behavior between the result of a TON addressing a timer data type and an RTO addressing a timer data type when they were disabled by a rung condition out false state. Yes, you do see a difference. There is timing involved in the next step in the lab project manual. And so I'll read it first and then we'll work at it. While observing the outputs of both sets of rungs, switch input 0 to the on state, wait a second or two, and then switch it back to the off state. So we're on for 2 seconds and went back off. Well, because we didn't reset the RTO instruction and its timer data type, it didn't accumulate. But you notice the TON did start to accumulate, and then when input 0 went back off, rung false, it cleared and went back. In the manual it says, well, there's trouble in River City, folks. One of them did not reset. Well, we knew that was going to happen. I mentioned it. Now, when you did the lab manual, you probably did not know it was not going to reset, even though you probably looked at the name Retentive and wondered what that was all about. This is the first of several differences between the TON and the RTO and how they manipulate the members of their instance of the timer data type. The RTO does not reset when the enable bit goes off. There is no false execution for the RTO instruction as there is for the TON instruction. So this is your second instance of seeing two instructions that kind of work together or are similar. One of them has a true and a false execution, the other does not. An OTE, output energize, has a true and a false execution. A OTL, latch output instruction, has a true execution and no false. There is another instruction, the OTU, unlatch, that you have to use in conjunction to turn that bit off. So this is a very similar situation. Let's add another rung of logic to our logic here. I'm going to add it and then we'll be back. Now we have a reset for the RTO, rung 6. I told you to add this rung of logic to your routine. It doesn't have to be the last rung. Location in the logic at the most could affect the reset by 1 scan time difference, 20 microseconds or so. In some logic, this could render other logic non-functional, but not in this instance. So just for grins, we'll go back to the main program, properties, monitor. You see we're still around 20 microseconds. So even with all of this logic, and you bumped it up to 24 once in a while. We really haven't changed the scan time of this program very much by adding these rungs of logic. Get rid of that and go back to business here. While observing the RTO instruction and its associated control bits, switch input 1 to the on state and back to the off state. Now with the digital field device simulator, I can just reach over and push the push button so quickly that you didn't even see it go on. So I'll push the button and hold it down so you can see input 1 is going on. Now remember, IN00, IN01, that's nomenclature from the digital field device simulator as we have it marked. If you've seen it, we have 6 toggle switches, vertical, with 0 at the top, 5 at the bottom, and then right next to that we have a row of lit push buttons. All 6 push buttons are wired or in a circuit with a toggle switch. The top one, of course, is a special input, so you can have normally open or normally close, or maintained on, maintained off. The rest of them are just normally open push buttons in parallel with a toggle switch. And it makes learning a lot easier if you have push buttons and toggle switches to work with. And you can see the lights real easy. But if you're on a shoestring budget, oh, I can appreciate making every dollar count. What happened? When you hit reset, it reset the RTO, meaning that it cleared the done bit and cleared the accumulate, just like the TON. Now let me turn on input 0 and hit the reset button. Okay, this is for 10 seconds. watch the RTO and input 01 down there at the bottom. See, the RTO is accumulating. I pushed the resetting, it reset. See, every time I hit the reset, it keeps accumulating. Now that would be the same, I'll reset them both, if I did the on delay. If I let it accumulate and then turned off and made the run false, it resets. But notice the RTO did not. TON on, resets. Now the reason I did that is, and I'll reset the RTO again, is so you can see the difference between those two instructions. Did you see any difference in the values of the instances of the timer data type that each of these two instructions are addressing? So I'm going to do that again. I'm going to flip it on, then flip it off. Now, look at the RTO accum, or I should say, look at the timer data type, whose name is my time also. It's a accum value, which is 2,951 milliseconds, and you look up here, at my time it's 0. Now I'm going to turn this on again. Notice this started from 0, this keeps on going from where it stopped. And every time the run goes false, it stops accumulating, but it doesn't reset. So it retains the accumulated value. Very, very handy instruction for certain applications where you want to accumulate the on time of something that is intermittent. In other words, you want to do something after it's been on for 90 minutes, but not 90 continuous minutes. The 90 minutes might be spread over 2 or 3 days. But when 90 minutes have accumulated, whether it's emptying a tank or lubrication on a shaft, whatever, you want to accumulate the actual runtime. Do you see any difference in the values of the instances of the timer data type that each of these two instructions are addressing? Yeah, you see a difference. Right there, RTO is 7128 and TON is on. If I turn it on, they're different. Did the accumulate member of the timer data type addressed by the RTO start accumulating at 0? You could say yes or no depending on whether you're talking about the first time or this time. I would accept either answer there in class and explain that if you said yes, it started accumulating at 0 when after you reset it. No, it started accumulating where it stopped if you didn't reset it. When you switch input 0 off, what was the accum value of my time also? Well, whatever you wrote in there. And what is the value with input 0 in the off state? That again depends on where you start and stopped executing that logic with input 0. While observing the accum values of both instructions and the done bits, switch input 1 to the on state and let the timer instructions time out. We'll leave the RTO and see it times out right away because it was already at 9,000 or so milliseconds, so there was only 1 second left. We'll wait until my time times out. At what value did it start accumulating when you switched input 0 to the on state? That is, at what value did the RTO start accumulating when you switched input 0 to the on state? Well, it could have been anything. But mine was like at 9,000. Did both of the instances of a timer data type reach the done state during the same program scan? The answer, of course, is no. It's always possible that you had them both reset to 0 or something like that. If you did, well, then they both reached during the same scan. So if I were to reset, turn it off, reset, they're both at 0, right? And then let them both, you'll see that they're accumulating at the exact same identical rate. They'll reach the done state during the same program scan, but what we were demonstrating was something more like this. RTO, stop, it's at 2532. Now, obviously, the RTO is going to reach the done state 2.5 seconds ahead of the TON, like now. Then there's the TON. Look closely at the screen capture in the manual. I captured the online in the run mode logic between my time done equals 1 and my time done equals 1. One is done and the other is not. The RTO is done and the TON is not done. What two members of the timer data type have their values retained when the RTO run condition goes false? What two members? The accumulate value and the done bit. Okay, that's it for timers for now. We'll go back to timers later on when we start doing a challenge.